question. Wait, that's weird. The solid lies between planes perpendicular to the x-axis at x equals -1 to 1 again. The cross-sections perpendicular to the x-axis between these planes run from the semicircle. Well, that's a semicircle because we have y is equal to the square root of 1 minus x squared. If we square both sides, we got y squared equals 1 minus x squared. You don't have to do this. I'm just showing you that this is the equation of a circle with a radius of 1. Now that's the base. That's the shape that is on the xy axis. And the plus is the top of the circle. The minus is the bottom of the circle. And we're going from -1 to 1. So there's the top of the circle, and the negative is the bottom of the circle. Oh, that's not bad. Huh. Circles are hard to draw. The cross sections are circular discs with diameters in the xy plane. So what we end up with is it's a ball. Because the cross sections are circles, the bases are circles. So we have this circle right here. Something like that. That's the cross section. So the area is pi r squared. Well, we want this in x because the cross sections are perpendicular to the x-axis. So the area, let's see, the radius goes from here, the x-axis, and it goes to just one of the curves. So you could go to the top or you could go to the bottom. Either one's the radius, but we try to avoid going to the bottom because then we have to mess with a negative. We'd rather not. So that's pi times the radius, the length of the radius is sitting right here. Because if you're way out here on the end, that's a tiny little circle. If you're towards the middle, then that's a much bigger circle, right? So it's following, the radius is following this curve. Well, that's the square root of 1 minus x squared squared. So that's pi times 1 minus x squared. So that's the answer to 1a. Any questions on that one?
How do you know that they just want the area and not for you to integrate and use that way?
In exercises 1 and 2, find a formula for the area of the cross sections of solid that are perpendicular to the x-axis. So they're not saying anything about finding the volume.
Okay.
In the instructions at the top just says find a formula for the area.
Okay.
That's how we know. B. Yeah, I mean, you can go on your own if you want to, or you can watch this, of course. The cross sections now are squares with the bases. So now, the base is still a circle. They say 2 semicircles, but altogether that's a circle. And now, we're looking at squares. So the area is side squared. Now we have to find the length of one of the sides. Well, from here to here, that's only half of the length. Now if we added the two together, if we added this plus that, in theory, that should be the length, right? Well, one's negative and one's positive. When you add those two together, you're gonna get 0. You're not gonna get the length that we want. So what we do is we just take one of those and we just double that. So now the length of a side is 2 times the square root of 1 minus x squared. We double that length and we get the length of the entire side. We can't add the two together. We get 0. So 4 times 1 minus x squared. Don't forget to square the 2 as well. So that's what they're looking for an answer. And then you could continue on and integrate that right there. They're saying, no, good enough. You found the area. We assume you know how to integrate. Letter C. They even give you a hint on letter C if I remember right. Semicircles. The cross sections are squares with diagonals in the xy plane. And it says the length of a square's diagonal is square root of 2 times the length of its side. We'll get back to that. Let's try to get somewhat of an accurate drawing. So here's one of an infinite amount of squares. There's the diagonal, and there's the square. You got to kind of visualize this in 3 dimensions. The area is still side squared because it's still, the cross section is still a square. But now we have to come up with the side. It tells me the length of a square's diagonal, D, is equal to the square root times the length of its side. So the side times the square root of 2. Well, we want S. We want this to say S equals. So S is equal to the diagonal over the square root of 2. Now if we can get the diagonal in terms of X, we got it. Well, the diagonal runs from the bottom curve to the top curve. And that's just like we did before. So now the area is equal to, let's see, the diagonal. Why am I losing focus here? S equals. The diagonal is 2 square root of 1 minus x squared over square root of 2. But I have to square that. So 2 square root of 1 minus x squared over square root of 2. There we go. I have to square that. That is 4 times 1 minus x squared over 2. So it's 2, 1 minus x squared, like that. There we go. That's the cross-sectional area. Isn't that one fun? How about the last one? Everybody got it? That wants to get it? Wow. I think this one talks about equilateral triangles. The cross sections are equilateral triangles with base in the XY plane. So here is, there's one of many triangles. So the area is 1/2 base times height. Alright, so what do we got to do here? We got to get the base and the height in terms of x. That's our goal. If we have an equilateral triangle, these are all b's. Equilateral, they're all the same side, they're all the same length. There's the height, that makes this 1/2 of b. We want the height. So we have h squared plus 1/2, h squared plus, I want to square that, that makes it 1/4 b squared, must be equal to b squared. So a squared plus b squared equals c squared. And when you square that 1/2, it's 1/4. So h squared is equal to 3/4 b squared. So h is equal to the square root of 3 over 2 times b. Does that look familiar, square root of 3 over 2? Well, yeah, when you take an equilateral triangle, you get a 30, 60, 90 right triangle. That's right from your unit circle. So what? So what does that mean? Well, now I can write the area as 1/2 times b times the square root of 3 over 2b. I can rewrite the height in terms of the base. Well, now the area is square root of 3 over 4 times the base squared. And we've talked about how you get the base. The base runs from the x-axis to the edge of the curve. Now that's half of the base. So the area is equal to the square root of 3 over 4 times 2 times the square root of 1 minus x squared squared. So the area equals the square root of 3 times 1 minus x squared, because this will be a 4, that cancels with that 4, that's gone. So there's the cross-sectional area. Now if you wanted to find the volume, you'd integrate from 0 to 1, and you'd double that. Questions? It's getting a little clearer, a little bit maybe, I hope. I wasn't going to do this in first period, but I ended up doing this. I did, what's our next one, 3? I ended up doing 3 as well. So would you like to see that? Yes? Okay. Number 3, in exercises 3 through 6, find the volume of the solid analytically. The solid lies between planes perpendicular to the x-axis. All right, so these cross-sectional areas are lining up along the x-axis, which means we're going to integrate with respect to x. And I am finding the volume. So I'm integrating with respect to x. We're going from 0 to 4. The cross-sections perpendicular to the axis on the interval 0 to 4 are squares whose diagonals run from those two curves. The diagonals. That always makes that a little harder. There's the square root of x. There's negative square root of x. So it's a parabola. This is your x-axis. Here's your y-axis. Now they're putting the diagonals of the square, they're running from the top to the bottom. So now these are, so that should be a nice square. We're going from 0 to 4, we're told. 0 to 4. Now on the other one it said that, on 1C it said, the length of a square's diagonal is a square root of 2 times the length of its side. Well, we're integrating side squared, but with respect to x, not with respect to s. So it says the diagonal is the side times the square root of 2. So the side is equal to the diagonal divided by square root of 2. So if we can get that, we can square it and we got it. What's the diagonal? Well, the diagonal runs from the x-axis. That's half of the diagonal, right? But we can't add negative square root of x and square root of x. We can't add the two together. That's going to get you 0. So what we do is we take half of it, we take one of the curves, and just double that length. So the diagonal is at 2 times the square root of x over square root of 2. There's the length of a side. Now we can go back to the integral. It goes 0 to 4, 2 square root of x over square root of 2, and we're squaring that. So what we're taking the integral of is 4x over 2 dx, and the integral actually becomes pretty simple because now we're integrating from 0 to 4 of just 2x dx. I'll let you finish that. That one's going to take you 2 more seconds. Well, I might as well just finish it. X squared, 0 to 4. The answer must be 16. It is, it's 16. So the integral ends up being the easiest part, ironically. Questions on that? Give the rest a try. If you need help, I'm right here.
So, you know how when you sometimes I take it from school, why do you not have this?
I did. I'm just going from 0 to 4. I'm not using any.
It's on the other side.
If I was going from -4 to 4 and there's some symmetry here, then I would double it and just go from 0 to 4. Yeah, no symmetry here. Okay. Let me turn this off, guys.